Hello all, welcome again. Uh, Please subscribe to our channel if you did not subscribe to our channel by clicking subscribe button, and for personal notification press bell icon. If you really like the videos, please press the like button. In this series of STM32H7 there is this session is all about STM Chromate accelerator, which offers true hardware acceleration for graphical operations. In this session, we will go through the overview of the Chromate, key features, register to memory, memory to memory, and memory to memory with pixel format conversion, memory to memory with pixel format conversion and blending features, input pixel format conversions, and then YCRC color space converter, font special modes, output pixel format conversion, as well as blending, output configuration, foreground and background configuration, interrupts, low power modes, and application examples. So let's quickly jump onto the overview of the Chromate. The Chromate accelerator is built around a 2D DMA engine for fast data copy with specific functions to support pixel format conversion as well as blending operations between two planes. It also provides specific modes for managing anti-aliased fonts. The Chromate accelerator will offload the CPU for most of the graphical operations with a 1 pixel per cycle throughput, integrated pixel format conversion and blending. The Chromate accelerator is fully integrated in graphical stacks, making its software integration transparent to the user. So here is the Chromate structure. Okay, the key features are 2D DMA with graphical oriented features with 4 operating modes, namely register to memory for rectangle filling operation, memory to memory for 2D memory copy operations, memory to memory with pixel format conversion for bitmap drawing with format conversion, memory to memory with pixel format conversion and blending for bitmap or text drawing with transparency. The user can program independently all the parameters for the source and destination, the address of the layer, including size and position, the color format, the way transparency is managed. Okay. After this, we'll just quickly have a look at register to memory mode, which is used to fill a part of whole destination image with a specific color. Here in this figure you can see the color value is set in a register of the output PFC. Then rises the question, memory to memory mode. So this is the register to memory mode, and memory to memory mode is used to copy a part of whole source or image into a part or whole destination image without changing the color format, just as shown in this figure. So we have an image and copied image here through FIFO. We are copying memory to memory. So how about having a pixel format conversion within memory to memory? So memory to memory with pixel format conversion is used to do the same type of copying as memory to memory mode, but with a pixel format conversion. It can copy any input format to any output format. For example, here an ARGB 565 image into an ARGB 888 image without having to use the CPU. See, in this flow you can see we are not at all entering into any of the CPU. Just by using FIFO PFC we are just able to copy with pixel format conversion, PFC. Okay. So memory to memory with pixel format conversion and blending can happen this way. Memory to memory mode with pixel format conversion and blending is used to blend a part or whole source image with a part or whole destination image with a different pixel format. This is widely used to draw bitmap icons having transparency or fonts. See, we have a foreground image. One is in the form of cloud and another one is foreground image with a background, right? I mean, kind of background. When we are blending it, the output we require it. So it goes in both goes in separate FIFO and enters into the blender. Then via PFC, in FIFO, the filled rectangle is out here. So input pixel format conversion for each foreground and background layer. The format can be programmed independently. Direct mode fetches the RGB or ARGB content directly from the memory. Indirect mode uses an intermediate color lookup table to determine the color to be used during the copy or blending operation. All the input color modes are transformed internally into ARGB 8888 format to perform the blending operation. Here in this you can see like LB to CLUT, ARGB 8888 combination and A8 to register and then ARGB 8888 combination, ARGB 1555 into ARGB 8888 combination in this example. So how about color space converter? So YCBCR mode is one specific mode which enables a specific color space converter hardware to convert YCBCR data into RGB data. This block is available on foreground plane. This color space converter is used to copy or blend uncompressed data from JPEG decoder into the frame buffer. It allows to convert directly YCBCR data arranged in 8x8 pixel blocks into a linear RGB format. So all standard YCBCR chroma subsampling formats are supported from 4:4:4 down to 4:2:0. You can see here. This new feature offloads the CPU from this costly operation and makes it 10 times faster. Is this clear? Then we can move on to the font special modes. Specific modes can be used to efficiently manage text and fonts. Only the transparency value is stored in memory for rendering anti-aliased fonts. So you can see the difference here, A in aliased fast, alphabet A in aliased fast and anti-aliased font. The color is added during the pixel format conversion process and can be programmed by the user. These modes are very efficient for storing high quality bitmap fonts. Output pixel format conversion is another topic where converter generates the color for the destination independently from the source. There is no direct mode in output, as this would imply to calculate a color lookup table CLUT, which we discussed earlier in our previous sessions. Nevertheless, memory to memory operations without pixel format conversion PFC can copy data independently of their format. We discussed about CLUT in our LTDC session. I hope you understand. If you don't understand, go back to that video and please go through CLUT. Okay. So after this we'll talk about blending. The fully hardware blender allows to blend a foreground image and a background image with transparency. Here you can see in this figure, no? This can be used to draw bitmap images of any shape with a perfect rendering. 1 pixel is generated per cycle, making this complex operation much more efficient than if it was done by the CPU. The resulting pixel can be coded independently from the source thanks to the output pixel format converter. We discussed about it. So it would be great if we have an output configuration, isn't it? So working with area or output configuration, or so output configuration defines the work area for Chromate operation. The address and line offset parameters are used to select which sub area of the output is concerned. See this example, we have an working with width, working with address, working height and original width, original height, original address. So area of work is width, height. Output configuration is address, line offset, color format, BPP. So working address equal to original address plus X plus original width star Y star BPP. Line offset equals to original width minus working width. This is how we configure the output. So here comes the question: foreground and background configurations. The foreground and background layers have their own configurations for address, line offset and color format. You can see in this figure. This defines which area of the foreground and background layers are targeted by Chromate operations. So foreground here, address, line offset as per output and color format. Background parameters are address, line offset as per output. Address is also as per output and color format. Most of the time background and output have the same parameters. Most of the time. Let's quickly get on to some of the interrupt source to signal. No? Chromate accelerator has 6 interrupt source to signal: configuration errors, CLUT transfer complete, CLUT access error, watermark reached during a transfer, transfer complete, transfer error, no DMA trigger is used as the Chromate accelerator embeds its own DMA. You can look at the descriptions, and here I am giving you all the stuff. Then as usual in low power modes, Chromate is active in run and sleep modes. A Chromate interrupt can cause the device to exit sleep mode. In stop mode, the Chromate accelerator is frozen and its register's content is kept. But in standby mode, the Chromate accelerator is powered down and it must be reinitialized afterwards. So we'll have a quick look at an example application. Home alliances including connectivity and HMI, that is human machine interfaces, Chromate can handle HMI building. So Chromate accelerator is widely used in any graphical applications to compute the frame buffer without any CPU load and with a very efficient throughput. It can compose the whole scene with transparency and facilitate the management of animations. Text rendered is also accelerated, making it easy and efficient to manage anti-aliased fonts. So while trying it, you can also refer to some peripheral trainings of RCC, Chromate clock control, and Chromate enable reset in RCC, and Chromate interrupt mapping in interrupts, which will be discussed in the later sessions. So thank you for watching. If you really like this video to be useful, please click like button, and if you did not subscribe, if you feel so to get more information, please click subscribe button, and for personal notification please press bell icon. Thank you.